So let's talk about meteorites, and before you run away, don't worry, I will try to make it painless. So when we talk about meteorites, so basically this is what we do have. So today in the worldwide collection, we have more than 77,000 meteorites, and more or less 90% of them represent primitive asteroids that didn't melt, and melting is going to be very important here. So primitive asteroids didn't melt, and this is some names that you probably know. This is what we call the chondrite. And then when we look at asteroids that have been melted, we call them achondrites, so that's the E privative. And you see a much larger diversity with iron, stony iron meteorite, but it's only 8% of the worldwide collection. And you see a little gap in between that we're going to fill in with the primitive achondrite. So basically, primitive achondrite, they share both characteristics. We see some melting, but at the same time, they still have a chondritic composition. So that's how we're going to make the link between the two. It's only 0.5% of meteorite, and before you ask, yes, we still need new meteorites because we still find new type and rare type, so this is still ongoing effort. So practically, what does it mean? So this is something you know very well. We've been talking a lot about accretion, and then you start having asteroids to melt them, and then to have a core and mantle like Earth-like planet. So basically, what we find in the chondrite, there are tiny grains, presolar grains, chondrule CAI, that are actually witnessing the very beginning of the solar system. And then we're going to put them together, compact them, and this is what we call the chondrites. The chondrites are not the oldest asteroid in the solar system, but they contain the oldest grain of the solar system. But then we do have heating. Aluminium-26, iron-60, we're going to start heating the system. And then we're going to start melting the asteroid, so getting the achondrite. So we do have iron meteorite, we do have stuff from Vesta, for example, or the last famous one, Earth-Shesh 002 meteorite, witnessing the early melting in the solar system. And then the primitive achondrite, that's the topic of today, they're going to make the link between this state where it's heated but not yet melted, and then melting of asteroids. And something very important to remember, because a rock is a very poor conductor, we're going to heat a lot the inside of an asteroid and less the outside of asteroid. So keep that in mind. Temperature is always higher at the center of an asteroid. Why do we have those elements? It's just because we start the solar system with a budget for nucleosynthesis. So basically, Big Bang, you have nothing. You create elements in stars, and our solar system is going to start with a budget of stable and radioactive elements. So basically, when we start accreting, the solar system becomes kind of immune to adding new elements in the solar system. So of course, stable isotopes don't move anymore. Long-lived system, we still see some parent element today. And then the short-lived system, for example, aluminium-26, now they're totally extinct. But because they're going to decay very fast at the beginning of the solar system, we'll be able to have a very good insight of the processes at the beginning of the solar system. How do we do that? So we're going to use the radioactivity as a clock, actually. So what we do in the lab, you have the parent element decaying in the daughter element, and in the lab, we're just going to measure, we're going to measure, it's a little bit more complicated than that, but we're going to measure the amount of the daughter element, and then we can deduce the time between the beginning of the solar system and the time to see that we need to see the amount of daughter elements. And then we can use this aluminium-26, magnesium-26 system with a half-life of 0.73 million years. When I say just, this is a little bit more complicated than that, so we do a lot of lab work, so just quickly to show you what we do. We collect meteorites, we crush them, we separate them in powder and minerals. We add very nasty stuff on them to digest the minerals. So that's a very big issue we have, is what we do is destructive. So we're going to destruct the sample. And then you have very nice color. We're going to purify element by element, because you need to get very precise, a pure fraction of the element you want to measure. And then we're going to use fancy mass spectrometer. Of course, it's a little bit smaller than I would say it's big, but it's smaller than a telescope, but we do generate plasma, which is nice too, so this is something very nice. After all this work, you're going to obtain something that you might know, which is a chronology of the solar system. So we consider that 0 is the time of the oldest solid in the solar system, the CAI. We do have presolar grains. It's difficult to date them because actually it's a bit sad, but they don't have aluminum, they don't have magnesium. So they're very tiny as well, so it's very difficult to date them. CAI is by definition the beginning of the solar system. You have the chondrites. You can see that the chondrites, they're going a little bit later. And the reason is that if you don't want to melt an asteroid, you have to wait for aluminum-26 to decay. So that's the paradox of chondrites. They contain the oldest grain, but they are not the oldest asteroids. Then you can see iron meteorites, so you can see that very early in the solar system we have asteroids that have been melted. And of course, here you see a change of scale. We have much later formation of core, of big planets, and everything. So I told you that today we're going to investigate the primitive chondrites. So I've been using two types, Acapulcoites and Lodronite. They're coming from the same parent body. We know that because they're sharing the same oxygen composition. And the Acapulcoites have a very low degree of partial melting, 1 to 3%. And the maximum temperature they got is something around 1000 degrees Celsius. And Lodronite with a little bit larger degree of partial melting, but still the melt has not been extracted. And the temperature is something like 1200 degrees. Something that's going to be very interesting here is that the melting is very low. It means that I have to find a size of an asteroid that is not too big, not too small. If it's too small, it's not going to be heated. If it's too big, it's going to be totally molten. So the fact that those meteorites are clearly at the edge of the melting of an asteroid is going to give me a very strong constraint on the size of the asteroid. So this is the result, and I'm not going to spend too much time on it. So this is the kind of result we generate in the lab. You can see here we have the parent-daughter ratio, but it's aluminum-27 because aluminum-26 is gone. And then here you have the magnesium anomaly we generate by the decay. And then if you did a good job and the sample is appropriate, you see this kind of correlation that we call an isochrone. And that is giving you, in this case, the amount of aluminum-26 at the beginning of the solar system. It's a fossil isochrone. But because we know how much aluminum-26 we had at the beginning of the solar system, I know how much I have in the sample. Now I can calculate a delta time between the two, and I can see that the two Acapulcoites are 1.5, 1.8 million years after the CAI, and the Lodronite is 4.6 million years after the solar system formation. Then we can go and do some fancy modeling. So on this type of modeling now, I'm just going to investigate how an asteroid is going to be heated and then cooling down by the aluminum-26. So you have always the time here. Here you have the maximum temperature that is expected. And every time you see the higher curve is the center of the asteroid, so the hotter part of the asteroid. And then when you go down, you go to the surface of the asteroid. I've also indicated one Acapulcoite and one Lodronite with the arrow bar. It's a bit loud, but this is a logarithmic scale actually, so that's why it's a bit stretched. And I did this modeling for several sizes of asteroids, 35, 50, 100, and 200 kilometers. Now we have another constraint. I know the maximum temperature those meteorites have experienced. So I'm just going to look which one is the best. So that's a very simple approximation here. And what you can see is that the curve fitting the Acapulcoite, I need to go to this blue zone. And the curve fitting the Lodronite, I need to go to this orange zone. Basically, 35 and 50 kilometer size is okay. When you go higher, 100, 200 kilometers, you see that actually you delay the heating of the asteroid. So you go to a higher temperature, but you delay the heating of the asteroid. So basically, those are too big to be consistent with what you see. Oh yeah, one last thing. You may wonder why those samples are just plotted here at 400 degrees. It's just because you need, so what we did actually, it's not strictly speaking the crystallization. We did the temperature under which we have no diffusion anymore. And for those samples, this is 400 degrees. So basically, in conclusion, we do see very early differentiation of heating in the solar system, and the best fit we have is consistent with a parent body that has been formed very rapidly, less than 10,000 years after the beginning of the solar system. And that's very important because we need timing. So when we start accreting those pebbles, we need timing. So this is the timing for the formation. But then the point is that because we cannot grow too fast as well, we have also a timing for stopping accreting this asteroid. And then basically it's something like also 2 million years after the solar system. So it means in the modeling of making planetary formation, we need zones where we're going to be extremely fast at forming asteroids, but then at the same time we need to stop accreting them very fast as well. And then the most adequate diameter is 35-50 kilometers. So thank you very much for your attention.
Questions? Jackie, you go first.
Thank you. Very nice talk. At the beginning, you mentioned that the pre-solar grains couldn't be dated in part because they don't have aluminum and magnesium, but I don't understand how aluminum magnesium would help.
No, that's a good point. I was a little bit too optimistic on that. So indeed, if we want to date pre-solar grain, aluminum magnesium will not be very helpful on that. What we might look is at general nucleosynthesis. So for example, the amount of thorium. This is something we kind of know, and we can use it for dating the universe, actually, the Big Bang. So the problem is that they still don't contain thorium anyway. So it's still very complicated to measure. I know one study where they made some estimate, but it's still something like 5 plus or minus 5 billion years. So it's not going to be very helpful, unfortunately.
So I'm a little wondering about this 10,000 years after the formation, because it's hard for us to think about actually collapsing a cloud to make the disk and the star on less than 100,000 years. Yeah. So I'm trying to understand that.
No, that's a very good point. And when we had the result, at some point we're a little bit puzzled as well. The point is when you go back to this kind of diagram, you see that iron meteorites, which are differentiated meteorites, so you need the time to make something relatively big and then segregate the core, you can see that actually they go back to the formation of the solar system, which means that you need a process that's extremely fast and efficient to make the first asteroid. And then, as I said, some of them will stop, so you also need to be able to stop accretion.
It's like you're forming it during the protostellar phase.
Yes, yeah.
Okay.
That would be...
Just a quick remark. I think it doesn't start at the collapse phase. It starts at the ages of the oldest CAIs. That's the 0 point.
That's
right?
exactly the point. So basically, the CAI are actually not the first solid to form. The first to form will be a platinum group element, osmium, iridium. We cannot really date them as well. They're too small and too imprecise to be dated. So that's what I said. By definition, we put the solar system formation at the oldest CAI we have so far. But that's for sure that some stuff just happened before, slightly before that.
So, Eric Gaidos, University of Hawaii, it's a very clear talk, very nice. Is there some trade-off between the growth time for the body and the size of the body? Is there some degeneracy there, wiggle room? Having a larger body growing at
So the point is a larger body would start melting. So at that point, it's kind of difficult to put any constraint because once everything is molten, what's the depth, what's the size, it's kind of difficult to put some constraint. So that's why those meteorites are interesting because I can put a constraint of the non-melting or the edge of melting actually. Yeah. But once it's molten, at the very beginning of the solar system, you melt everything that's above 35 kilometers, everything is going to be almost fully melted.
Yeah. And then just a slight technical question. In your melting models, your parent body models, do you include the effect that when you start the partial melting, the aluminum actually preferentially partitions into the melt and gets removed.
That's a very good point. Some people have tried to include that. In the case of primitive echondrite, the melt has not been extracted, so everything is still staying in the same place.
In the meteorite, though. Yeah. Thank you.
Any more questions? I have a very naive question. So you dated this meteorite to be about 1.8 million years. We know that from planet formation perspective, by then there should be even like embryo formed. So I'm just trying to make sense. What's the linkage between this 35-kilometer body in the solar system versus those embryos which could have already formed within the first million years through pebble accretion? So what's the connection there?
The connection is that in this case, you need to be able to stop planetary accretion as well, which is not something that's very easy, because when you think about all the pebbles, everything you start creating should start growing as well. So at some point, what we're seeing here, it's going to be very fast to grow something, but we need to be able to stop it as well.
Sean Raymond, University of Bordeaux. Cool talk. This is a very simple question. So how confident are you of the different meteorites coming from the same parent body? And do you know the parent body? Or is that
so we don't know it, but they do share the same oxygen isotope. So it's commonly thought that when they do have the same oxygen isotope, they do share the same parent body.
You don't know which one it is?
No. All right, let's say thank Vinciane again.